This session will be chaired by Mayank, who is a research assistant professor of industrial and systems engineering at USC, and also a research team lead at the Information Sciences Institute here. So Mayank, the floor is yours.
All right, thank you, Philly. So I want to thank everyone for staying with us. We have a very exciting panel, and I'm super excited and nervous to be talking to three very esteemed figures in AI. And let me just begin with introductions to our panelists, and we will jump straight into questions. Before I begin, for the audience, if you do have questions, please feel free to put into Q&A, and we will try to ask those as we go along. We really want our audience to be engaged. And so with that, let me begin with Dr. Vered Schwartz, who is an assistant professor of computer science at the University of British Columbia. Her research interests focus on natural language processing with the fundamental goal of building models that are capable of human-level understanding of natural language. Dr. Schwartz has interest in computational semantics and pragmatics and common sense reasoning, and is currently working on learning to uncover implicit meaning, which is abundant in human speech, and on developing machines with advanced reasoning skills. Next, we have Dr. Katherine Havasi, who is the co-founder of ConceptNet that we have heard mentioned several times during this symposium due to its importance. In fact, ConceptNet was co-founded by Dr. Havasi with Marvin Minsky and Push Singh in 1999. And she has also done extensive research in word embeddings, transfer learning, multilingual, NLP, and machine learning. And she directed the Digital Intuition Group at the MIT Media Lab. And finally, we have Dr. Kenneth Forbes, who is the Walter P. Murphy Professor of Computer Science and Professor of Education at Northwestern. He received his degrees from MIT, his PhD in 1984. His research interests span across AI and include areas such as qualitative reasoning, and analogical reasoning and learning, spatial reasoning, and natural language understanding. And this is only to name a few. He has received the Humboldt Award, served as chair of the Cognitive Science Society, and was the inaugural winner of the Herbert A. Simon Prize for Advances in Cognitive Systems. So with that, I want to give a warm welcome to all three of our panelists. We're delighted you're here. And let me jump straight into my first question, which is that, and we get this a lot in our own work, which is, so there is some evidence that language representation models like BERT and GPT and so on are getting really good at common sense reasoning. So this is what the evidence seems to suggest on the benchmarks, but they also seem to mess up in strange ways, as a number of authors have shown. And so I want to ask each of you, how close do you think these models are to solving common sense reasoning? And I want to begin with Vered.
Thanks, Mayank. Yeah, so there's one major, I mean, there are multiple limitations. There's one major limitation that I feel like I'm always repeating, and I've been complaining about it since word embeddings. So because of the way that these models are trained in a sort of like distributional manner, they're trained to predict the word based on the context in which it appears. So they learn very well which types of words fit in each context, but they mostly learn about similar words rather than learning about more like they have a problem distinguishing mutually exclusive concepts that may be very semantically similar. So one example I like to use is if you take a model like BERT and you try to predict something like the color of the dove is mask, and then try to predict the substitute for the mask token, then it does predict a lot of color names because it knows that semantically it should be a color name, but it's not necessarily the correct answer because it probably didn't see that a lot in the corpus. So it predicts red, blue, green. The same thing happens with confusing different days of the week or months, or recently I worked on predicting time spans from time expressions. So if you ask the language model to predict which time of the day is afternoon, then it just knows that it should be some number in the, probably in the range of like 0 to 12 or 0 to 24. And but it doesn't really know, it doesn't really distinguish between the representation. All these kind of like groups of semantic groups of words are just really confusing for the models, and it's really it's a limitation if you use these models to learn about, to extract knowledge from them, where it needs to be much more accurate.
I see. Catherine?
I think Barrett is absolutely right. There are certain kinds of knowledge, and if you break down common sense knowledge into all the different pieces ranging from taxonomic to something like more folk physics, folk psychology, there are certain things like taxonomic knowledge that I think we can gather from, a build of the entire web, a corpus on the entire web. But there are a lot of kinds of knowledge that we're not going to be picking up through that we're not as good at. And if we're running sort of blanket accuracy, blanket prediction tasks, we're going to see the strengths and not the weaknesses. So I love things that break it out. Within what we know about transformer models today, there's been so much what I think is very interesting work, because I'm kind of a geek in that way. And into what's the structure, what's going on under the hood, what are these models doing? But I think we're still pretty nascent in a lot of that. And our ability to emphasize and explain and debias these models, we're pretty far from that in being able to actually go inside the box. And I think that's going to be super important and something we need to do before we're able to make real big forward jumps. Additionally, what we can learn from large amounts of data only works for certain kinds of common sense. If we think about some of the more physical tasks we talked about over the course of the symposium, we're not going to find a web full of data to be able to train one of these massive models on. So we're never going to get that common sense out of that. I think that's very important, and not to mention sort of domain transfer, which I'm sure we're going to get into in great, problem transfer, which I'm sure we're going to get into in great detail over the course of the panel.
Yeah.
Or some detail at least.
Ken?
So two examples, one from law and one from the physical world. So from law, one of my students who's a joint law student and PhD in computer science used GPT-2 as a baseline to compare against analogical learning. And it was pretty bad, like really bad. And the funniest answer was in one of the trespass examples, its response was, the plaintiff and defendant got married in divorce court. Now lots of things happen in divorce court, but marriage, not so much. Okay, that's one of the few things you know is pretty unlikely to happen. And they continually generate garbage like that. And the problem is the people looking at them are subject to the ELIZA effect, right? We tend to grant agent status to things that use language like us. And if you look, they're incredibly noisy. If someone reports a result at n, where n is bigger than 1, I think they ought to be required to report at 1 as well, because otherwise you don't really get a sense about how well the systems are doing. The other example is from the physical world. So we've got a model of conceptual change that can use language inputs or sketched inputs, sketched comic strips to simulate motion. It goes through the sequence of motion models that students go through. It can track, for example, if you're giving it explanations of the circulatory system that have particular misconceptions, and then you have it self-explain, it can capture 90% of the student transitions between those. There's no way the language models are ever going to be able to do this. Those require qualitative representations. And by the way, analogical learning is incredibly more data efficient and training efficient. We've actually started hybridizing that with deep learning a little bit to do things like visual relation detection. And we're competitive, but only have to touch the data once as opposed to tons of epochs every time. So there's a whole space of things to be explored, but you need representations that aren't just words, That's kind of a fundamental thing for human cognition.
Yeah, so it seems that all three of you agree that we're not we haven't solved common sense, despite what the benchmarks might be saying. There's still a lot of work to be done, and that brings me to the second question, which is related to this one and to your answers, which is, if you had to pick the most exciting line of work in common sense reasoning right now, and this could be something that is not being done right now, but that could be done, the single most exciting thing that you would like to identify, what would that be? What do you think is the most exciting line of work in common sense reasoning? And I'd like to begin with you, Ken, and we'll go in reverse order.
Okay, so here's a bet my group is making. Okay, so take a look at Atomic 2020. Okay. So you get this bunch of text that's chirped, and they puree it into a language model. Okay, that's one thing you can do with it. Another thing you can do with it is to try to use high precision natural language understanding to come up with small pieces that could be used by chaining with analogy. We call those common sense units. And we've actually shown that on the COPA, which is a test actually developed at USC for common sense reasoning, that analogical chaining with human supplied microstories in English that get translated into predicate calculus through a large ontology can actually do pretty well on a subset of the COPA. And now we're trying the same thing with the social IQ test from AI2 and Atomic. We're also looking at elemental cognition's glucose. And so the hypothesis is that if you have high precision conceptual representations constructed automatically from language, and you use analogical chaining on those, you can actually get effective common sense reasoning. That's a bet. It obviously could be wrong, but boy, it's really interesting to explore.
Catherine?
So really, from my point of view, I think that there's a lot that's exciting going on, and it's kind of hard to pick. So I have two things I want to talk about briefly. The first of which is, I think, a lot of work that's being done recently on script and interaction and social common sense. I think that's incredibly important. I think we're finally at a point where we can make some forward progress on this. There's been a lot of effort made over the years. I mean, I've done some of it. Many people have done it. That hasn't really amounted to where we want to be in this area. And I think we really have an opportunity. And I think we also have a lot of applications that could really benefit from some advancements in that area. The other thing I'm really excited about, some of the work in language and knowledge graph completion and knowledge graph expansion that we've seen. I know knowledge distillation is exciting. It's pretty early. A lot remains to be seen. How can we build out specific common sense knowledge graphs faster? But I'm a knowledge graph person, so that's definitely a very exciting area for me.
Very.
So I think it's similar to the other two answers. I think in terms of what currently works pretty well, I really like the comment model, and in general, I think it's a really good combination between the accuracy of knowledge graphs and the better coverage that you can get from a model that can provide not just on-demand inferences for new inputs, but also make them context aware. And so that's like in terms of what already works. I'm also seeing a lot more work on multiple modalities recently, and I think that's a really exciting. It's an exciting research direction, and it's a really good way to overcome the reporting bias and the limitations of what you can learn from text alone.
All right, that's so lots of exciting work to be done. So I did, speaking of knowledge graphs, and that leads me to my next question. So we have been seeing a number of interesting synergies on knowledge bases, knowledge graphs, and language models. The two that I'm thinking about are, there have been some work where the knowledge is being used to augment the language model in some way. And there are other pieces of work where they are showing that the language model itself can be used to maybe extract knowledge, right? And so that's the sort of the augment the knowledge graph so in the other direction. So how, in your view, does explicit structured knowledge in knowledge graphs help language models as they continue to get bigger and better? So for instance, is it more, is it to increase the performance, or is it more that it could make it more domain specific, that would be better domain transfer? So what is the most promising avenue for explicit structured knowledge and knowledge graphs to help language models for common sense reasoning? And I'd like to begin with you, Catherine, on this, since you mentioned knowledge graphs.
Yeah, I mean, I think that this is long been an area where I see a lot of applications from common sense all the way back to when we were looking at embeddings models and we were doing retrofitting and exfitting into those models. When we moved to transformers, I think there's been a lot of interesting ways of taking structured knowledge and changing transformers, both through sort of masking-based training and through some more structural improvements. But I don't think we're really at the point where we know completely what the best way to incorporate structured models, structured information is. You know, there's a lot of promising things. I don't feel like I've seen what I think is the final form of it. There's a couple places where I think structured knowledge combined with knowledge graphs is really important. One of them is within domain adaptation and few-shot learning. I think there's been a lot of work over the years from embeddings and the stuff that I worked on in that era all the way to modern times, where we're looking at proof that we can basically do better transfer when we've incorporated structured knowledge graph information into the model. That if it's a better base for what happens later down the line. And I think that's tremendously exciting. The other place I see it is actually in explainability, right? Knowledge graphs are, and I think that's something when we talk about common sense that obviously came up in the last session, but I think a huge role for common sense is to provide and to help the explainability of these more difficult to understand models. You know, earlier we were looking at attention graphs and trying to say, well, how can we explain those better to individuals who have to use them who are non-technical, right? And if we think about a knowledge graph, if you're in a situation where you're interacting with the user, that format is much, much more easy to understand than anything that could possibly come out of a deep model or a language model. And I think that interoperability between structured knowledge and these models is going to be key to sort of building an understandable bridge.
Ken?
So I think the explainability point is absolutely crucial because explanations are relational structures, right? So if you can't have a connection between antecedents and a consequent, then you're not in the explanation game really. And so that's kind of key. I find the hallucination property of language models to be really quite odd as to think of them as a basis for a system. So for instance, in natural language dialogue, the Microsoft dialogue systems don't use a large language model for that because, as the designer said, if someone said, I want to schedule a meeting for Thursday, the language model will say Friday, because that's in fact more likely in the corpus. Okay, so what are they actually good at? Well, they're really good at, for example, if you can find some way to tie things to semantics that is crisper, and they can provide evidence for that. So we've used BERT in two different explorations. One where we're using it to basically estimate disambiguation in a high precision deep understanding parser. I mean, a full stack natural language parser. But because we can tie it to frame semantics, BERT can actually say, well, maybe it's this one more likely, right? And that's something that the language model is probably pretty good at. I mean, it's early days, we can't really tell yet, given our experiments. And we have a paper in AKBC about using BERT in conjunction with analogical reasoning to try to do information extraction. So I think as a component of the mix, they can be valuable, but the idea that that's going to be the primary component, you somehow inject the knowledge into it to make it work better, I would not bet on that. I'm glad there's other people exploring it, right? I mean, part of the point here is there's a huge, rich, interesting space, and people ought to make bets and explore different things. It's way too early to say, yeah, this works, this doesn't work.
Yeah, very.
So I was gonna mention explainability too, so I'm glad it came up. But I think that there's something a little problematic about this, because it really depends on the way that the knowledge from the knowledge graph is incorporated into the neural model. Because I've seen some work that, including my own, but I'm always trying to hedge and say, I don't know, it's not necessarily explaining what the model is doing. Because a lot of the times what you actually want to say is that I can say that the model had access to this knowledge from the knowledge graph, but we don't actually know in what way it was using it, if it was using it at all to make the decision. If you find a way to incorporate it in a way that you're certain that the knowledge is being used and that the explanation is faithful to the model's internal decision process, then that's good. And in referring to your other suggestion about what it can improve, eventually we wanted to improve the performance on the end task. But I think now part of the problem that is, I mean, it's kind of hard to get improvement on many of the tasks, not because they don't need this kind of external knowledge or because the language model captures all that knowledge already, but mainly just because of the way that our benchmarks are built right now, that most of them are multiple choice or classification tasks that are very easy to game by just overfitting and learning some spurious correlations between the inputs and outputs. And it's just really hard to beat any kind of large neural net or transformer-based model trained on a lot of data. So often when I do work on incorporating knowledge from knowledge graphs, so I say, okay, well, maybe we're not going to get state-of-the-art performance, but at least it's going to be explainable in a way. But I don't think we're seeing the I don't think it's a realistic picture of how much performance gains you can actually get from knowledge graphs. I think once we have more challenging benchmarks, we're going to see more improvements from incorporating knowledge.
Yeah, and that leads me straight into the fourth question, which is really on evaluations. And there's been so much conversation on this. I mean, I can personally attest to that through the Machine Common Sense program that is being funded by DARPA right now, that we've had many conversations across the program on evaluation. And so with that, let me actually get into that question, which is that there's been a lot of conversation about properly evaluating common sense reasoning. You know, should we be going for, should we abandon multiple choice? Should we go for generative, and so on? And so my question is that do you think that we need a Turing test like evaluation for testing whether a machine truly possesses common sense? And what would a really good evaluation look like? And since you brought this up, Vered, I'd like to start with you on this. Like, what would be your notion of an ideal evaluation to really help us to figure out, does a machine have common sense?
Yeah, so I don't think we necessarily need one kind of benchmark that measures progress on all kinds of common sense reasoning types. So I don't think we need a Turing test like benchmark. I do think that it's good to have like small specific benchmarks that either test a specific reasoning mode or a specific type of common sense knowledge, like physical or social. But in terms of the format, I think, yeah, I think we should probably move on from multiple choice and classification tasks, or if we keep using them, we should probably have a much more strict evaluation with and maybe change the way that we build our data sets, because I think some of the problem is that, you know, like when I learned, I took a basic course in machine learning, I've been told that overfitting is when you get a good performance on the training set, but then it doesn't help you when you evaluate on the test set. And that's not what we see in machine learning today, because the way that the benchmarks are built is that typically you would crowdsource the data set and then you would just like randomly or in some more sophisticated way split it to train and test, and then you get this really the same distribution, the same kind of annotation biases and in both the train and test set. So we could continue doing working on multiple choice and classification tasks, but we need to have much stricter evaluation. And in terms of generative evaluation, I think that's a really good thing to work on. And obviously, you have the advantage that it's much harder to game generative evaluation because you can. It's much harder to guess an entire sentence than to guess a label. And it's much more flexible. It's much more nuanced. Much more similar to the way that humans reason, I assume. Because we're not often provided with answer choices. But of course, the disadvantage right now is that it's just much harder to automatically evaluate for the same reasons, because I guess telling that or being able to determine that a free text answer is correct is almost as hard as being able to solve the task. At the very basic level, you need to be able to handle lexical variability, but sometimes you want to support two different answers. So I think the two directions we need to take is first is stricter evaluation for discriminative tasks, and the second is evaluation metrics for generative tasks.
All right, Ken.
So I work with psychometricians some, and they think of machine learning as almost corrupt, okay? Because the idea that you're training to the test, it's like, no, you never do that. That's just crazy. And when they say human performance, it's not calibrated against humans the way a real psychometric test is. So it's very misleading. So the data set addiction and the soda fetish are really hurting the field, okay? We're getting these local maximums, we're getting these systems. For instance, there's a paper from Elemental Cognition that points out, if you think about the reason you want these tasks, doing well on the benchmarks does not guarantee in any way, shape, or form. Like human level reading comprehension, no, we do not have that. That's a joke. And yet you'll see papers claiming it. So we have a serious, serious problem here. And ACL knows this. They actually had a workshop on evaluation this year. And so there are people who are sounding the alarm and trying to step back from the precipice. So what I think is necessary and is shockingly expensive, and alas, it's even worse than you would expect. So in addition to generating answers, you also need to support drill down. You need to support asking the system why it believes that, show its work, show its thinking. Yeah. Okay? Because sometimes the reasons people believe something are a little bit crazy. And if you look at the sort of machine explanation sometimes, we've seen things in our system where it gives us the right answer, but in fact, the reason it believes that is not sensible, okay? And so ultimately you want that. Look, the real test isn't that you can do a benchmark. The real test is, can you do a job? And so finding jobs that are low stakes where nobody dies if you get them wrong, but force them to interact with people in ways that will expose their foibles. I think that's ultimately what we're going to have to move to. It can't be static. It can't be a single test. It can't be a single benchmark, because people are very good at solving puzzles, and they will crank up their systems and set up their pipelines in order to solve that test. And then doing all that work is exactly the sort of thing that you don't want humans to be doing.
Yeah, Catherine?
Absolutely agree with everything that's been said. I don't think one benchmark, I'm not gonna say the same thing again, but I don't think one benchmark is gonna cut it. I don't think many of the things that we're looking for a holistic common sense system can easily be benchmarked in the way that we benchmark. And using one system always simplifies or reduces the problem to something that can be gamed, or something that can be, even if it's not overfitting in the strict sense of the word, building systems that are hyper-tuned to solving a particular evaluation that, when they're let loose in the real world, don't really have an impact, and don't have an impact towards broader AI goals. And I think that's an issue. And so I think, in a sense, we think of systems that can pass more holistic benches of benchmarks, potentially systems that were trained to do one task, how well do they perform on another task? And I know that there are some attempts to make benchmarks in this area right now, but they're all very, I would say, very early, and don't require the same level of reasoning that, you know, human level tasks would. Right. And I think it's very difficult, and it's very difficult to do automatic evaluation of some common sense tasks. Generative evaluation, it's really hard still in an automated way. And taking the human out of that evaluation, there's a lot of folks who are working pretty hard and have been for years. And I bounce between industry and academia, right? And on both sides, people are working on trying to solve the generative evaluation problem. And there's a lot that's happened there, but we haven't seen a good way of doing it. So it becomes a question of, do you need a human in the loop for evaluation? How do you deal with subjectivity in that case? How do you deal with bias? And it's becoming incredibly difficult to try to solve this problem.
Yeah, so let me switch to a question that we have from the audience that is related to this, or to the previous question. So the question is from Bart, and what he's asking is, what common sense areas are reasonably covered? I mean, I guess he means language models, but I would also add language models and evaluations. What common sense areas are reasonably covered by language models and evaluations, and what areas are weakest? So are there areas in common sense that you feel are being under-evaluated, or where, I mean, or that are more reasonably covered? And so I will begin with Catherine.
So I think that there are a lot of evaluations for sort of semantic similarity type tasks, for anything where you're looking for sort of a fill in the blank, language completion problems, those kinds of things. But when you get to the more difficult questions, especially around sort of the physical common sense, the social common sense, the generative common sense, those are really areas where I'd say there aren't good evaluations. In some sense, we're almost looking at downstream uses in some of these cases, right? Mm-hmm. So you can, I know, especially within the debiasing community and debiasing work, there are models and techniques that perform very well on certain tasks, but then when you use them in downstream tasks, the bias comes back, right? And I think there's been some really interesting work on that, because downstream models complete fill in the blank, right? You're filling in the blank. So you took the bias out, that's a blank, the downstream model is going to fill in the blank, right? And so when you hyper evaluate to one specific task, you risk missing things like that. So I don't know if I would say, I think holistic view of evaluation is more what's missing than one evaluation specifically.
I see. Right.
I'd like to answer this question as to what types of knowledge is encoded in language models and what isn't. So the last I checked, I think language models were not very good at causes and effects. I think it had to do with reporting bias. So it was less about what is not captured by the model, because it's not often mentioned in the corpus, and it was more about what is more often mentioned in the corpus than it is frequent in real life, which is like what is more newsworthy. So every time I tried to start some narrative and let GPT-2 continue it, it always ended up with someone going to the hospital or having an accident or something really more exceptional than daily, because it probably didn't really see a lot of boring day-to-day stories in the corpus. So I think that really, I mean, I'm not sure that's the only issue, but I think it was really hard to generate causes and effects with language models. On the other hand, it was pretty good at generating definitions. I think especially the models that were trained on Wikipedia. I'm not sure how much it adds to just, retrieving the definition from Wikipedia, but if you build a model and the only thing you use as a source of knowledge is a language model, then you can pretty much trust it with definitions. And I think there were other papers showing that it was pretty good at detecting predicting hypernyms of words. I think all kinds of semantic relations. I mean, some of them were good. Of course, it also depends on how you extract knowledge from it, because it's very sensitive to the phrasing of the prompt. So these are like two different questions: what knowledge it captures, and what how accurately you can extract that knowledge from it. And there are areas of knowledge that it doesn't capture enough, like perceptual and physical knowledge that is not often discussed in text.
Yeah, that's those are very good points. Ken?
David Israel used to make fun of my group by saying that we were the Japanese French School of Artificial Intelligence, because we thought that you could have an AI system learn about the world entirely through comic strips and language, okay? So the language model people have actually gone further. They said, no, our hypothesis is language is enough, okay? Well, thank heavens someone is exploring that hypothesis, but I think it's not on the face of it very plausible. So I'll just, instead of going about more general examples, let me just show you a simple example. So someone needs to cut a branch off a tree, okay? And there's a real example. So they rent a chainsaw, and the branch is very high, and they don't have a ladder that goes that high. So they get a long rope, and they tie one end of it to the chainsaw. They throw the other end of it over a branch higher than the branch they're trying to cut. And they pull on it. They start the chainsaw, they start it swinging, and they pull the rope up. Okay. Now, I'm sorry, language isn't enough to really get why this is such a crazy idea. And by the way, there was a lot of bloodshed, but the guy didn't die, okay? But this is something that's very spatial. It's easy for you to understand a linguistic description, easier if I have gesture to communicate some spatial information in a visual understanding way. But the idea that I'm going to get that entirely out of language seems pretty dodgy to me, okay? And so you need language, okay? So if you're going to make a social being that's human level intelligence, it has to have language. It has to have language. You have to have counterfactuals. You have to have logical numerical quantification. You have to have quotation. You need all that powerful expressive stuff that language gives you. But you also need spatial knowledge, and that can be through vision, that can be through sketching. There needs to be a spatial modality that's tied to language if you're really going to have the breadth of mental models that humans exhibit.
Yeah, and that leads me to, so we have 7 minutes remaining, and so I'd like to give everyone a chance to, you know, for the very last question, which is broad, but I think it's related to the second question, which is, where do you really see common sense reasoning research in 5 years? So do you, which is different from what's the most exciting line of work. So in 5 years, do you sort of expect, as hard as it might be to predict, some of these problems to get solved? And would it depend on some fundamental innovation? Or, you know, or do you think that the route that we are on now, it's just a matter of time, and in 5 years, the transformers and knowledge graphs and so on, we'll have figured out, you know, how to do common sense, or how to make machines that do common sense in 5 years? Or is it going to depend on a fundamental innovation? It's kind of where the question lies. And so just I just like to go in the same order we started with. So Vered.
So I'm never good at predictions, and I think it might be because I don't know, maybe lack of imagination. But I'm pretty sure we're not going to be still using language models, not as the main or the only tool. I think we're not going to be. So it seems like in the last few years, every time there's something new that the entire, at least the NLP community, I don't know about the rest of machine learning. Now it seems like more than just NLP, that everybody converges to. So right now it's transformers. Some years ago it was word embeddings, and LSTMs somewhere in the middle. I don't know if we're going to have something that's like a centralized solution for everything. I actually hope that we're going to have different methods, and we're going to see more diverse ways to get knowledge, to incorporate it into models. I think probably a part of it is going to be working with multiple modalities, and hopefully maybe taking inspiration from other fields, like, for example, how people learn about the world, how children learn about the world. Yeah, hopefully there's going to be more synergy between different fields instead of like trying to reinvent the wheel with machine learning.
Yeah, Catherine?
Yeah. I mean, I think absolutely it's not going to just be large language models. I think we hopefully in 5 years, I'm hoping we're going to move away from one model or one technique alone can solve a problem to being able to utilize and have things work together and just be tools in the toolbox to thinking of how to get to a solution. And I hope to see a lot more of that. I hope to see a lot more multimodal work. I think that there's a lot that can be gained from that. And I think at a more practical level, I know we talked earlier about, taking structured knowledge, putting it into knowledge graphs, taking information from one representation to another. I think we're going to get to a point, and this is my prediction, I hope in 5 years we're going to get to a point where we can do that in a more principled and understandable way, so that some of the uncertainty that Vera talked about earlier is something that we have a little bit more under control. I want to see more explainability become part of a standard of what is expected of an AI system between now and then. That's something that I'm not sure if I'm predicting, but I'm hoping is going to happen, and we'll see. And maybe the only real prediction I have is that in about 5 years' time, we're still going to be having this conversation about evaluations and how hard they are.
Yeah, we hope so. But with that, let me move to Ken for the closing thoughts.
Should I? Okay, so I think in 5 years, actually, we will have open knowledge networks that have considerable amounts of common sense knowledge, and those will be tied to various other kinds of models. So part of what's gone on is the same kinds of enabling conditions that let deep nets actually start doing cool things in 2011 are now finally coming true for other technologies. The idea that there would be billion node knowledge graphs in the hands of industry was kind of viewed as crazy in the 1980s, right? And yet we're here. So these things can scale nicely, and the real big challenge now, I think, is going to be reasoning, accumulating things that are inferential knowledge, because factoids isn't enough, right? Wikidata is not most of what people would consider common sense. So you need inferential knowledge, multimodal knowledge, as everyone's been saying. And you need to have effective reasoning techniques that go with that at different points in the scale, right? So rapidity when you're dealing with the physical world directly in a robotics context, more subtle if you're dealing with the social world in a negotiation. And so reasoning systems that actually capture those different trade-off spaces is going to be one of the big things I hope we're going to be focusing on, because we will have enough knowledge graphs around and enough other techniques around to where that makes sense. And that becomes the big frontier.
All right, and on that note, I think we are right on time. With 1 minute to go, I would like to thank all of our panelists, and I hope everyone gives them a virtual round of applause. We love to follow all of your work, so we're really looking forward to seeing what you come up with and just following your work. And I encourage the audience, everyone in the audience who's interested in this, you should absolutely follow their work on what's happening. And it's basically the first labs in which you will probably see many of the innovations that we discussed today. So with that, I want to just hand it off to Philippe and thank our panelists again for giving us their time and their insights this afternoon.
Great. Thank you, Mayank, for chairing this session, and also for seamlessly taking care of the time. I think you managed to make it entirely on time. I thank all the speakers again, Vered, Catherine, and Ken, for participating.